All right, this is actually probably like the first of 4 videos I'm about to record, all sitting down in one setting. Granted, this one will be different. They're not just going to be 4 Xanadu videos, but we did get to Hamiltonian 4 last time, so we're continuing on in this series. And worth noting is that Xanadu saw that I was close to completing um, their code book, and so they decided to add some more content. I think it's very, very kind of them to give me more content to produce, which is nice. I jest, of course. I'm sure this has been in the works for at least a couple days. So yeah, actually, this reminds me of something that I should do. All right. Anyway, getting into it. Let's see if we derive the Trotter-Suzuki decomposition. Poor Suzuki, whoever that person is. I know trotterization. It's hard to say, but I've never heard of Suzuki before. Let's give them some historical credit that they are lacking. Okay, I don't know who they are. Let me look up who this is named for me. Who is Suzuki? S-U-Z-E. Here we go. Does not cite them. Now let's look this person up. Right. Surprising, this is so weird for someone as presumably famous as they have their name on this famous decomposition. I can't find out much about him. But that's enough of the distracting. Components. We'll go over here. We are once again simulating some little electrons. So all we have to do is some rotation weights. Let me check my mic actually. Yeah. Okay. We also checked the recording, 3 minutes. Okay. Okay, now we can do RC negative. Let's see, it says 2 copies of this in circuit form. I'm gonna be 100% honest right now and say I definitely thought this was the letter Z and did not realize that was just a number 2. All right. All right, now if you want to represent unitary matrices as products of exponents, it's very hard because this is only true if they commute. So you have to do them many, many times before that becomes true if they are not commutative. All right, so now we want to write a circuit to trotterize the evolution of 2 electrons with Hamiltonian 1. Oh, okay. Oh, okay. It's All right, so for n times, for I n, we want to repeat this. Let's check out what this is first. See, that's the amount, the gate. All right, so let's see. We have negative I t h bar over h. So we have negative theta over 2. So we have I there. So we want to do 2 times this quantity, right? So that will mean theta p. Okay, so we're going to do out poly root. We're going to do theta in this case is 2 times alpha. I don't know how to do. I don't think this is going to work, but and then wires, I assume, is the third one. I guess we can just separate them out. It's probably easier. Copy this. All right, done with that. Now we need the poly note beta. We actually 3 times beta. So I think this should be negative. And then we want, I don't know, xx squared equals 0. Maybe that's gonna work. No, I didn't think it was. Okay, Oh, right, I forgot the time component. So we have t over n times t over n. That's what I forgot. Okay, still isn't giving it right. At least we know this is an error now, so it is a correct. It shouldn't be negative. No. The reason I think it's negative is because it's right, the negative IT h bar, and this is negative. Okay, so let's look at this. Exponent e to the negative I t over n times h bar over h bar over h. Okay, let me see what's going on here. I'm just reading to the right side. So let's see. verify. I don't want to do that. Let's look at this. Yeah, this is basically the Hamiltonian we have here. And you can separate these two out trivially because Z0 and Z1 obviously commute. So what am I doing wrong here? Let's look back at this example. Let's see. Let me check to see. Did I already do this? I forget. Yes, I did. So what is going on here? Maybe you don't actually need the 2. No, you do. This is very intriguing. I don't know. Okay, well, before I go trying to look it up, I will actually skip line. I'll actually try to do it out. All right, so we have our e to the negative I theta over 2 theta over 2p. So this is our gate. And then we're going to say, okay, our task is to simulate this e to the negative I t over n h1 hat over h bar e to the negative I t over n h bar hat 2 over h bar n times. All right. So now we can see that we now have to match this here. We are given, in this case, we'll just say negative alpha, right? Because it's negative, so we're carrying it over to get h, the Hamiltonian over h bar. Negative alpha c0 plus c1. All right, so we have that mapped on. And now, so for all of this, we need theta over 2 equal to negative alpha t over n. So we simply multiply by 2, we get theta equals negative 2 alpha t over n. Apply it to z0, apply it to z1. I'm getting the same results. Alpha z0. Does this one need to be swapped with the order? Oh, yeah, that's why. I just had to swap the order of them because I didn't know which order they were writing it in with the desired goal. But that's fine. So now we are writing 2 we have the coefficients negative h bar, h bar times BE over 2ME, 2 times E, and then h bar squared over 4 times J. Actually, I'll leave it like this. H bar squared over 4 times 0. And we will repeat this. So now we will have 1 and 2 observations we have. Let's check exactly what this is. Oh, we have to actually write out the Q and L dot poly Z 0 plus Q and L dot poly Z 1. Then it's x0, x1. Okay, yeah. So Q and L dot poly x0 Q and L dot poly x1 Q and L dot poly y. Y 1, this should actually be 0. And then keep it out dot poly Z 0 poly Z1. Alright, there we go. Okay, what is going on? Oh, why can I not? That's a nice thing is you can't debug anything. Oh boy. Let's see. Negative h bar BE. Are you not allowed to do pluses? Is that disallowed maybe? Okay, well then I will repeat it. Then I will do comma. Okay. See h bar BE over 2ME. Oh my gosh. Why does this keep happening? What does this even mean? I don't understand. I really wish it let me print things. That would make this so much easier if I could see, right? Like, I guess I could open up a new tab or something and execute the code, but then I have to get everything set up. I do not want to do that. I wish it just let me print things. I have to specify new device. Oh my gosh, that'd be so annoying. See, Z0, Z1, X0, X1. This comes in X, Y, Z. J0, J1, J2, H bar squared over 4. Okay, I don't want it. I'm going to see instead if they have any see this is H5, okay. Ah, here we go. Oh, see, this person did the exact same thing that I did. Oh no, not exact. They have the I over it's the total time. Um, but I guess it's actually 5.3. H3, H2, H6, H6. Okay. Wow. Is that what it is? Google Collab. Do not care what collab is. I'm just going to run pip. This is, and I have to sign in. Actually currently using a Colab notebook to run some code for something else, so I don't want to log in. All I have to do is make this Hamiltonian. What is going wrong? I can't print debug it. I have the negative h bar be over 2me. H bar be over 2me. But its Hamiltonian must be written in terms of write a function that returns h bar over L. Okay, no. No. I do not. Oh my gosh. Oh, it's so annoying that I can't debug it, and as far as I can tell, this is correct. Okay, here's what I'm going to do. I'm going to pause the recording, which is not something I would normally ever do, but I have to set up an environment to work in. Which is going to take a little bit. All right, I have now set up. I've not done anything. I was going to do something, so I didn't look like a fool, but I'll look like a fool and not do anything. And all I've done is just set up a new virtual environment that has PennyLane installed, and that's all I did. I just didn't need that to be, that would just be a waste of time to record it. So you can see I've just copied over the exact code and put a print statement in. And so, yeah, what's going on here is just this. So if I, let's see, so if I run it, oh, no, if I run desktop pipe, well, now you know that I used to play Heroes of the Storm. We can see what I think is going on is these are qubit terms. This is some sort of Hamiltonian. I don't know why it's doing that. So let's go over to the code. And see, I have so many things open right now. First, I think we can resolve this to be alpha. That might make this easier. That doesn't change anything, of course. It's just a handy little, you know, piece of, I don't know, something that you can do. Now we have to look at, I'm going to try just separating these poly-z's out real quick. Let's see what that yields. All right, so we can see, oh, I'm not sharing that, oopsies. Maybe, here's what I'll do. Oh. No, that's not going to be really visible. No, it's not. You can see that that has now fixed it. So I will copy this code back over to the code book. Now we can see that it says it is not giving the correct answer, which is good because that means that, it's good because that means that we have established that the Hamiltonian problem has been resolved. If I show this again, so I copied it back over, and now we can see that it simply says it's wrong, which is good. This is excellent. I will now try what I wanted to before, which is to see if in fact that it wants h bar over h. And it does not. Oh, it does. See, it actually wants the Hamiltonian over h. I don't know why you can't put sums in the Hamiltonian constructor, but you can't. So, fun fact for anyone trying to do this at home, don't try to put that sum in there. You have to separate them out. It seems like you should be able to do that, but you can also just use the function that they have built in, approximate time evolution, handy. So here's what we're gonna do. We're gonna say ham equals close spins b a. And then we're gonna say UML dot approx time evolution takes as input Hamiltonian, ham, time, and n. All right, excellent. We have now successfully done that task. This is already at 29 minutes, so I'm going to stop it and say that I sincerely hope that they allow people to print things in the future. I guess maybe it doesn't matter because people who are using this probably already have Penny Lane on their computer. I did not because I do not use Penny Lane that much, so I guess maybe it's not a real problem. But there you go, only got through one today. That was That was a slow one. I struggled a lot, I'll admit it.